Okay, excellent. So, very warm welcome to everyone to this Proteus Seminar Series session. It's a pleasure for me to introduce Fay Dowker. She's a professor at Imperial College London, and she will talk about a topic that is very close actually to the research topics discussed in our research group, namely being and becoming quantum gravity. So thank you very much, Fay, for being with us today, and I leave it to you.
Thank you, Sylvia, for inviting me. It's a real pleasure to be here. I wish it was there in Barcelona or even in Rome or Milan or wherever your project actually is, but maybe some other time in the future we can meet face to face. That would be a real pleasure. So I'm going to share my screen, I think. Let me see what happened there. Sorry, I think I need to open this file which got closed. After all this time, I'm still not, and I'm going to go to full screen. Good, can you see that, everybody? Sylvia, is that okay? Okay, so as I said, I can't see you, but if you have a comment, a question, clarification, then please do interrupt me. Sylvia, can you just check that I can hear you, at least, if you speak? Okay, I can't hear anybody.
No, you can hear me right now, I think.
Okay, good. Okay, yeah, I can hear you. Good. Excellent. It's just a little disconcerting when there's absolute silence, but so I'm going to be speaking about the approach to quantum gravity that I work on in the context of this ancient dichotomy between being and becoming. And in fact, they're actually intertwined in this story. 3 dichotomies, all of them ancient, not just being versus becoming, but what I've called objectivity versus subjectivity, and then atomicity versus continuity. And you'll see how those other 2 dichotomies become intertwined with the main topic of being versus becoming. So it is indeed very ancient, probably ever since we have records of people thinking about the nature of the world. This debate about the nature of time has been raging. So I've just chosen 2 examples of the 2 positions of being versus becoming, these 2 attitudes to what time is, or even the nature of reality as a whole. So the first one is, I don't even know whether this is who I'm actually quoting here, but it's something. It's a point of view attributed to Parmenides, but maybe someone reporting on what Parmenides' view was. So that view is that what is the universe has no beginning and will never be destroyed. It is whole, still, and without end. It neither was nor will be. It simply is, now, altogether one, continuous. The alternative perspective, that of becoming, is illustrated by this example. I've chosen an example, the example of the Buddhist doctrine of dependent origination, almost as ancient, if not as ancient. And this is a quotation from a book called Buddhist Logic by Shabatsky. There is no matter, no substance, only separate elements, momentary flashes of efficient energy, perpetual becoming, a flow of existential moments. And this dichotomy, this debate is ongoing, it's contemporary, it continues. And I've chosen another couple of examples to illustrate that it indeed, this debate continues. So on the side of being, that the passage of time is an illusion and the world simply exists in a timeless way, I've chosen this quotation from Paul Davies. He's a theoretical physicist who works on quantum fields in curved space-time. So Davies says, the flow of time is an illusion, and I don't know very many scientists and philosophers who would disagree with that, to be perfectly honest. Presumably, the explanation for this illusion has to do with something up here in your head, and is connected with memory, I guess, laying down of memories and so on. So it's a feeling we have, but it's not a property of time itself. Time doesn't flow, that's part of psychology. And on the side of becoming, the position that the passage of time is not an illusion, I've chosen this quotation from a paper by the philosopher of physics, John Norton. And the title of his essay is Time Really Passes. Time really passes. Our sense of passage is our largely passive experience of a fact about the way time truly is objectively. The fact of passage obtains independently of us. Time would continue to pass for the smouldering ruins, were we and all sentient beings in the universe suddenly to be snuffed out. We have no good grounds for dismissing the passage of time as an illusion. It has none of the marks of an illusion. Rather, it has all the marks of an objective process whose existence is independent of the existence of we humans. So, there's no consensus. Still, even today, there's no consensus. But it does seem to me, at least anecdotally, that the majority view amongst philosophers of science and physicists is indeed, as Paul Davies claims, that the universe is a block in which past, present, and future events have the same status. The arguments for the block are strongest when they are grounded on our best current science, and I'll say more on this in a minute. The arguments for becoming, that the passage of time is real, are mostly composed of appeals to intimate experience, subjective evidence. This evidence, although subjective, is undeniably powerful. Nothing is more fundamental to our experience of the world than its temporal nature. We experience one thing and then another, and then another. But we disagree, the lack of consensus arises because we disagree on whether that experience should count as empirical, and hence the lack of consensus persists. So, what does our best science say? Oh, it changed slide without me doing it. So, what does our best science say? What are the arguments for the block? The strongest arguments that one can make for a block universe point of view for being. Well, let me take a step back before giving you our current best science. Let's take a step back and talk about what time used to be thought of as being in Newtonian space-time. And I've called this le temps perdu because I claim that in pre-relativistic Newtonian physics, time, meaning time as a process in which events actually happen, was lost by being spatialized as merely a fourth dimension. So what do I mean by that? Well, here's a kind of picture of Newtonian space-time. Newtonian space-time, and it's kind of a chunk of it. Of course, Newtonian space-time is infinite in time and it's infinite in space as well. So this cartoon shows space depicted by this two-dimensional slice with these galaxies in it. at each moment of time. So I've just chosen 4 discrete moments of time to depict space, and these spaces are copies of space, are just stacked up one above the other, and there are continuously infinitely many copies of space at continuously infinitely many moments of time along the continuum time axis. And together, all these spatial slices form a 4-dimensional space-time. It's 4-dimensional, however, the geometry of Newtonian space-time is peculiar in the sense that the geometry of space is completely separate to the geometry of time. Time is simply a real line. That's its geometry. It's just a real Euclidean line. And space is just real Euclidean 3-dimensional space. And if, for example, we consider this world line illustrated by this red line here through space-time, where a galaxy, say, starts at this position in space at time t equals 0, is at this position in space at time t equals 1, etc. If we want to know how long it takes for the galaxy to get from here to here, then it's simply 3 units of time. So if these were in seconds, say, then that would be 3 seconds. And that's true of any world line. So long as it starts on this slice of space here and ends on this slice of space up here, then 3 units of time will elapse along that world line, no matter what that world line is or where it goes in space. So time is just a 4th axis. It's become spatialized. We're used to the idea of timelines. They abound everywhere. If you watch any kind of program about history, then they usually draw an axis, a 1-dimensional line, and mark off times on that line, or times during history on that line. So this is the Newtonian pre-relativistic concept of time. It's a dimension, it's an axis. So this is completely different from the notion of physical time in relativity. General relativity is our best theory of space and time. It replaced the Newtonian picture, the Newtonian worldview, and it's objectively, empirically a better theory. It explains more, it explains the data better, and it has replaced the Newtonian picture as our best understanding of space-time. And here I've drawn a chunk of an Einsteinian or Lorentzian space-time in general relativity. And there's no longer any slices of space, because space in GR doesn't exist. That concept of 3-dimensional space is gone. There is, in GR, physical time that elapses along world lines. So here I've drawn one. This red dot down here is the position of some galaxy at some moment in its history. And it traces out this world line as time passes for it and ends up at this position in space-time later on. And the amount of time that elapses along that trajectory for that galaxy in space-time is calculable in GR if we know the world line, and it's a quantity called proper time. And it depends on the world line. So if we have another galaxy which starts at this red dot and ends at the upper red dot, but the galaxy goes along a different world line, then a different amount of proper time will elapse along that world line. So that the picture is completely different, the world picture is completely different to the Newtonian view. Proper time is a local concept. It pertains only to world lines. I have my proper time, real physical time, elapsing along my world line, and so do all of you, and so does everything and anything that exists in the universe. Physical time is proper time. There is no time axis, There is no physical time coordinate. Time is not a dimension. It is local to a world line. Time is completely different from space. I know that it's often, the revolution of relativity is often expressed as a unification of space and time. That in some sense is the case, in the sense that the space-time in general relativity is a fully four-dimensional entity. You can't divide it up into space and time. But it's not true in the sense that space and time are not equivalent concepts, or even the same type of concept. There is time, but it's local along world lines. And there's no space at all. Three-dimensional space in GR is absent. There's no concept of physical three-dimensional space. There's no concept of physical simultaneity. There's no concept of a physical global moment of now. So consider this event here, this blue event. That could be like snapping your fingers, popping a cork, a supernova explosion, for example, in the galaxy at that point along the world line of the galaxy. So that is an event in space-time, but there's no concept in GR of a set of other events in space-time which are simultaneous to it. That concept just simply does not exist in GR. So the space-time, a four-dimensional physical world containing events, world lines, four-dimensional field configurations. There are no persisting 3D entities or substances. There are only correlated patterns of events in and of four-dimensional space-time. Okay, I'll pause there. Ask if there are any questions at this point. Okay. So that has led many to take on board, to adopt the block universe view of space-time, of the universe in general relativity, in which the universe simply exists as a four-dimensional block from the beginning, if it had a beginning, to the end, if it will have an end, in which all events, past, present, and future, are there in the block. And that's it. Everything is laid out once and for all. And as an examples, here's a cartoon. Here's this star down here is the event of me being born. This star up here is the event of me dying. This is my world line that I trace through space-time. And here's the green world line of some other entity. These blue world lines are the world lines of photons. Oh, sorry. And that's it. The universe it simply is, in Parmenides' words. And here I've made a example of the kind of discussion that can happen. And I have had discussions very like this. And the two discussants I've called the blockhead and the broadhead. Now these terms are due to the philosopher John Ehrman. I learnt them from Jeremy Butterfield. So a blockhead is someone who adopts this block universe perspective in general relativity. And the broadhead, Broad named for the philosopher C.D. Broad, is resisting this point of view. So here's a discussion. The blockhead says, events happen in the block. Look, there is a girl walking her dog. There is a tree growing, and there is a supernova exploding. And the broadhead says, no, the block is static. It corresponds to events having happened, not to them happening. The blockhead said, yes, it does correspond to events happening. The broadhead says, no, it doesn't. And it just goes like that. Yes, it does. No, it doesn't. Yes, it does. And I have had these discussions, and this is a debate that's going nowhere. And in fact, I think that at our current stage of understanding, we can't resolve this question. But with our current understanding of science, accepted science, for which there's a consensus in general relativity, we can't resolve this debate. This debate will just continue like this in a kind of fruitless way. However, general relativity is not the final word on space-time, in the sense that we know general relativity does not accord with our best understanding of matter, which is that it is quantum mechanical. In GR, we have to assume that matter is classical, but we know that's not true. And so the question arises how to reconcile our understanding of matter with our understanding of gravity and space-time. And that's the realm of quantum gravity. So in seeking a theory of quantum gravity, we're seeking a theory in which both our understanding of space-time as in GR and our understanding of matter as in quantum theory can coexist. And it's in this quest that the heuristic of becoming has played a role, as I will explain. To do justice to the temporal nature of our perception, whilst maintaining the four-dimensional nature of the physical world in GR, a growing block seems to be needed. And this concept is associated with the philosopher C.D. Broad, which is why in the argument, the blockhead was debating with the broadhead. So what's called for is a process of becoming for space-time, in which space-time grows and in which the past is fixed and concrete and the future has yet to become. And the physicist and quantum gravity researcher Raphael Sorkin has suggested that this growing block can be realized within causal set theory. In fact, it motivates some developments in causal set theory, which is a discrete approach to the problem of quantum gravity. And it can be realized in a way that does justice to this lack of a global time in general relativity. So I want to say only a couple of things about space-time discreteness. I'm not going to argue for it here or justify it. I'm just going to assume it for now. So the idea is that space-time is discrete in that there is a smallest indivisible event, a space-time atom, literally an atom, an undivisible event. And the observable universe is made of 10 to the 240 of them. 10 to the 240 is an estimate based on the idea that the discreteness kicks in at the Planck scale. So each space-time atom corresponds to a unit of 4 volume of space-time, which is Planckian in extent. The discreteness being proposed here is space-time discreteness. So these space-time atoms make up 4-dimensional space-time. It's not spatial discreteness, because space doesn't have any role in general relativity. It's space-time that's the real thing in GR. Well, so we have these space-time atoms that space-time is comprised of. What structure can bind these atoms together so that they can form an approximate continuum Lorentzian geometry? And the answer that Raphael Sorkin and others have proposed is causal order. So a causal set is a discrete causal order. What does that mean? Well, think about the continuum first. Here's a cartoon of a piece of the continuum space-time. Space-time in GR, the continuum, has a causal order. That is the information about which events in space-time can causally influence which other events. And this causal order is fundamental to understanding GR. For example, a black hole is defined in causal terms. It's the boundary of the causal past of future null infinity. and events that happen inside the black hole cannot causally influence events outside the black hole. So the entire understanding of black hole physics is in terms of causal order. So here's a picture. This event here, D, it could be a supernova. This world line, this blue world line here is the world line of a photon that travels from the supernova and reaches someone's telescope here at event A and is detected. And then the astronomer tells someone, or and it's recorded in a physical review article at event B in the future. So there are chains of causal influences, and all of the information about which events can influence which other events, that's called the causal structure or causal order of the space-time. The idea of causal set theory is to discretize this concept. And the hypothesis is that continuum space-time is an approximation to a discrete partial order or causal set. And this has been proposed independently several times in the history of quantum gravity by 't Hooft, by Meerheim, by Bombelli, Liemeyer, and Sorkin. So causal set is a discrete order. So discrete just means that there are a set of elements, which are the space-time atoms, which I've labeled A, B, C, D, E, and there are causal relations between them. So D precedes C, and C precedes E. D also precedes A, and A also precedes B. The order relation in a causal set is transitive, so D precedes B because D precedes A, which precedes B. So causal relation is catching. So D also precedes B. I could draw an arrow between D and B, but I don't need to because it's implied by the two arrows from D to A and from A to B. It's directed because there's an arrow, so the direction is from the past to the future, and it's illustrated on the page by upward going edges on this graph. So an upward going edge means that the lower vertex precedes the upper vertex. So in fact, I could delete these arrowheads on these edges. The direction of the arrows would be implied by the position on the page. So going up the page is going from the past to the future. So a causal set is a transitive directed acyclic graph formed of vertices, which are the space-time atoms, and the order relations or causal relations between them. And the idea is that our observable universe is a very large and complicated causal set comprising roughly 10 to the 240 of these vertices or space-time atoms with a very large complicated web or network of causal relations between them. So if the universe really is one of these causal sets to which our apparent continuum is just an approximation at large scales, then we have a new object to play with, and we have to come up with new ways, new laws, dynamical laws for such an object, for such a discrete thing. And here the heuristic of becoming played an important role in the development of a class of models for the dynamics of these causal sets or transitive acyclic directed graphs. And these models, due to David Rideout and Raphael Sorkin, are called classical sequential growth models. So in a classical sequential growth model, a causal set grows by a random process of continual births of new space-time atoms. The space-time grows into the future by the accretion of new space-time atoms. So space-time atoms are born and then they exist. They don't die or disappear. They just exist forever after that. the order in which the elements are born is a partial order. So here I've drawn two copies of the same causal set. So you can see that the structure of these two graphs is the same. So they are the same causal set. They represent the same discrete space-time. They're Hasse diagrams. This is where you don't draw on edges which are implied by the edges that already exist. And the direction is implied by the position on the page, which I've illustrated here. So it goes from the past to the future. So that I could draw arrows going upwards on all these edges, but I don't need to because they're implied by the convention of past being at the bottom and future being at the top. So this is the same causal set, the same physical structure with two different labelings on them. So in this left-hand copy, this element here is 0, this one is 1. So if I was to read off the labels in order, I'd go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the labelings on this side are different. So there's 1, 2, 3, sorry, 0, 1, 2, 3, then 4 over here, then 5. So you can see there, it's just a different labeling. Whoops, sorry. The probability, I said that these classical sequential growth models are stochastic, they're random processes. So you don't get the same causal set when you run this process. You get different ones with certain probabilities. But the probability does not depend on the labeling. So the probability of this causal set labeled like this equals the probability of this causal set labeled by this. And that's analogous to the action of a space-time in general relativity not depending on the coordinates. The physical order in which these causal set elements, the space-time atoms, are born is the partial order that they have in the resulting causal set. So element labeled 2 over here is born after element labeled 0, because that relation, that order relation, is there in the causal set. It doesn't matter what these are labeled as. That order relation is there, and that means that element 2 is born after element 0. But element 2 and element 3 are not ordered in the causal set. There's no order relation between 2 and 3, and so there is no fact of the matter about whether element 2 is born before element 3 or whether element 3 is born before element 2. That question is physically meaningless, in fact. They have no ordering. So the order in which the causal set elements are born is a partial order. And you can see that although this causal set here on the right is labeled differently, exactly the same thing is true. This element labeled 1 is born after the element labeled 0, and it's not born before or after the element labeled 5 because they're not ordered. So let me say that again. The physical order of birth is the partial order that those space-time atoms have in the causal set that grows. All the other label information is unphysical. In physics, the terminology that's used is that information is pure gauge. It's a way of labeling things, but it doesn't have any physical meaning. Now, what this means is that there's no such thing as the space-time that exists, not even a changing, growing one. There's no objective God's eye view of the result of this growth process. So why do I say that? It's because of these unrelated elements, so 2 and 3. So if I were to take a snapshot of this growing causal set after, let's say after 4 births, then the causal set that will have grown after 4 births would be this diamond. It will be, and this one, let's say 5 births, okay. So 0 would have been born, 1, 2, 3, and 4. So it would be this diamond and this disconnected one over here. That would be what the causal set that existed after 5 births. The causal set that exists after 5 births on this side is different. It's this one. It's 0, 1, 2, 3, and 4. So it's this chain here on the left and this separate element here, 4. So there's no way to compare there's no way to say objectively what the causal set looks like after 4 births, because with the different labelings, you get a different answer to that question. So there is no objective God's eye view of the causal set at any finite stage of this growth process. Are there any questions about that? I'm going to say that again a little, but are there any questions at this point?
There's just one quick question. In the second labeling, it looks like 2 is objectively before 3, but in the first labeling, it doesn't.
Yes, that's right. So that's because 2 is just a label. So this space-time atom that's labeled 2 over here on the right is not the same space-time atom as the space-time atom labeled 2 over here on the left. So what's labeled 2 on the right is what's labeled 8 on the left. So there's a causal isomorphism between these two causal sets, in which 8 here on the left gets mapped to 2 here on the right. So that those two space-time atoms are physically equivalent.
Okay, I think I was giving too much importance to the label because of the way you described them as marking the order in which things come into existence. But
so they don't mark the order in which they come into existence. That's the point. So because the order in which they come into existence is a partial order. So it can't be given so that choosing to label them as with the natural numbers endows them with the order of the natural numbers, but much of that information is unphysical. It's a gauge choice. So yeah. So another way to say that is that when I said stop the process after 5 elements have been born, that's physically meaningless. It doesn't. There is no physical stage which physically corresponds to 5 elements have been born. That has no meaning physically.
thanks.
Okay, thank you for the question. Are there other questions? Okay.
So you have 10 minutes left.
Yes, thank you, Sylvia. Thank you. Raphael Sorkin has called this dynamical model, or this type of dynamical model, asynchronous becoming. It's a model of a becoming process, in which causal set elements or space-time atoms are born, but they're born asynchronously. They're born in a partial order. And there are 2 completely different types of physical thing in this model, in this dynamical model of causal sets. There's the growing causal set itself, and there's the birth process. They are different. They're very different. The birth of a space-time atom is not a space-time atom. They're different things. They're of a different quality, but both are physical in the model. The process corresponds to things happening and to time passing. So there's both being, which is the causal set, and becoming, which is the process in a CSG or classical sequential growth model. In this model, we gain something that we didn't have before, which is a physical passage of time. That's the process. But we lose something too. What we lose is the God's eye view of the physical world. There is no such thing, not even a picture of a growing physical world. The causal set that exists is subjective. It's subject to each birth event. The past of the atom being born exists. So each atom that's born has a past, and that's a past of actually existing other space-time atoms, who's subject to each local moment of now for you. So a local now for you, your past exists, all the events that happened in your past. Subject to each local moment of now for me, my past exists. And that is all. There is no sense in which there is a causal set which exists in an objective way. So being, the causal set, is subjective, and becoming, which is the process, is objective. So in a CSG, classical sequential growth model, there are both subjective and objective elements. And then I said that there are three dichotomies intertwined in this story. Well, we've seen the dichotomy of atomicity and continuity. If causal sets turn out to be successful, then there will be both atomicity and continuity. But the continuity will emerge as GR emerges as an approximation at large scales. And the atomicity is fundamental, so they're not on the same footing. I just want to mention here just a list of things that to hang maybe a discussion on in terms of the concepts of process and discreteness or atomicity. It seems to me that these are entangled with each other, and it may be that discreteness is actually necessary to make sense of a process view of the world. So I've already mentioned dependent origination. That's a discrete process. These separate elements, momentary flashes of efficient energy, a flow of existential moments, implies, though I'm no scholar of by any means of Buddhist, of early Buddhist philosophy, it implies that this dependent origination process is conceived of as being discrete. Then, of course, Zeno famously, and I think that he belonged to the Parmenides school. His famous paradoxes are, as I understand them, arguments for why motion or change is impossible in a continuum. Then, in more recent times, there have been many causal set-like suggestions for new ways to conceive of the universe, new ways to conceive of space-time. I'd like to highlight the work of David Finkelstein in his series of works on what he called the space-time code. And he's very motivated by the idea of making process a central concept, and the space-time code that he developed was indeed discrete. Then there's Lee Smolin and Marina Cortez, even more recently, who have proposed a model of what they call energetic causal sets, again, in which the process of becoming of the causal set elements corresponds, in their view, to the passage of time. And then just more generally, there's the rise of the algorithm of digital computing, and I'll just mention Stephen Wolfram's program, which has very much a flavor of process and the coming into being of a growing discrete universe. Oops. Right, so that frustrating discussion, I claim, could be more fruitful now. We have a new concept. So the blockhead still says events happen in the block. Look, there's a girl walking her dog, there's a tree growing, a supernova exploding. The broadhead says, no, the block is static. It corresponds to events having happened, not to them happening. Blockhead no, it corresponds to events happening. And the broadhead can now say, the broadhead now has something concrete to hang their argument upon, something to compare to the block, something new to offer, which is the birth process. So the broadhead now says, compare the block to this classical sequential model of growth for causal sets, in which there is not just space-time atoms, but the birth process as well. And it's the process that corresponds to happening. And this is missing in the block. So here are just some concluding remarks. The future physics of quantum gravity may be able to provide a physical correlate for our subjective experience of the passage of time. The hypothesis that space-time is discrete at very small scales provides new possibilities, laws of growth for space-time, and causal sets are an example. The process of the birth of new space-time atoms can do justice to the lack of a global now in GR. And models in causal set cosmology have demonstrated this. This birth process is the passage of time. And there's both becoming, the process, and being, the ever-growing discrete space-time. The physical world has both objective and subjective elements. The becoming process is objective, but what exists, space-time, is subjective. There's no God's eye view of 4D space-time as it is. Then questions how necessary is discreteness to process to this process view? And what about the quantum? Oh, that's a big question. I've given it 2 question marks there just to emphasize. And then I'll end with this thought. In a relativistic worldview in which space-time grows by an asynchronous process, you are your past. You are continually growing as more events happen and become part of your past, part of you. You are different now than you were an hour ago because more has happened, and those past events are now part of you. Thank you for listening.
Thank you very much for your presentation. We can start with the Q&A. I have here Carl.
Okay, that was a very nice talk, and I enjoyed it. As someone who is a former blockhead, now trying to be a broadhead, I want to get something from the talk and something that can help me on my journey. But I just want to ask you to clarify the connection between the becoming or the process idea that's part of the story and the discreteness, because that I just don't see. To give you context, there are philosophers like Mauro Dorato and Steve Savitt who have been trying to look at the standard block and just say, no, there's still becoming in there.
Yes.
It's just that it's perspective dependent. So you pick a place in space-time and then things are happening there, and the past is all what's real for that point. And so there ought to be some difference now with the discrete causal set model, but I'm not sure I see what it is.
Good. To the extent that someone can make sense of asynchronous becoming in the continuum, I think you're right. I mean, you could say that in general relativity or in a continuum model of space-time, that space-time becomes, and it becomes in a partial order. You just add on top of what we already have in space-time, we add a new thing, the process. And in fact, there's a philosopher whose name I've forgotten, who wrote something almost exactly like that. I'll look up the name when I've stopped sharing my screen and everything. And I think that if one can think that way, then kind of that's great. But I can't. And that's something which I find difficult to explain, except in these terms. So when I think of the birth process in the discrete sense, it all builds upon, hangs upon my concept of a single space-time atom coming into being, that it's not there and then it is there. So it doesn't exist and then it does exist. And everything, all my understanding of this process hinges on that. It hangs on that. If I can conceive of one space-time atom coming into being, I can conceive of many. A finite number, arbitrarily large finite number. So there's one and then there's another. So that is something which I can conceptualize. I can hold it in my mind and understand it and work with it. The idea of a point in space-time in the continuum coming into being is something I find extraordinarily difficult, because you have to say, what is the continuum? The continuum is, well, it's a point in a space-time, in a manifold. Well, what's a manifold? So a manifold, in order to understand a manifold, you have to understand the real numbers. Well, what are real numbers? You have to understand real numbers. Well, there are many different ways to construct the real numbers. There are equivalence classes of Cauchy sequences of rational numbers, or they're Dedekind cuts in the rationals. So all of that when a point of space-time comes into being, when it becomes, it has to come into being in a way that locks it into this continuum with all that structure. So all that continuum structure. And I just can't imagine, that is just too difficult for me to conceive of. I just hugely struggle to conceive of, because it's sort of a modern version of a Zeno paradox. I just can't, I can't conceive of becoming in a continuum. But maybe other people can, and to that extent, maybe it is, it's possible to have a process view of becoming for continuum space-time. It's just not possible for me.
Thank you.
So Giuliano.
Yeah, thanks for the talk. Certain philosophers that discussed the causal set theory, like Chris Buttrick and Nick Haggett, give an interpretation of the model in terms of super time. So they say that there is the ordering relation, the partial ordering relation between the space-time atoms is the super time, and then you have the local time, which is the proper times of the word lines in the block. Yeah. Now, I had the impression that you were sort of resisting implicitly this kind of interpretation because you were sort of like insisting that you don't really have time in the block. And if you don't really have time, simply means you don't have coordinate time as a physical reality, then of course that's fine, but then one might still think that that's compatible with the super time interpretation. But so I was just wondering whether you have some thought about it, and a bit more specifically, if you so regardless of whether one by the super time interpretation, there's still the question of why a property like directedness should be inherited by the timelines in the block. After all, the theory just tells us that there is directedness as a property of the relation between the space-time atoms, although it's a partial order, but as you said, as a direction. But why this temporal direction should be also property of the timelines in the block? So why the fact that simply one space-time atom is born after another one, being the case that the temporal, the timeline curve that goes through them is directed.
Okay, so
there was two questions mostly.
yes, yeah, I gather that. So yes, I don't understand this concept of super time. So if you take the part of the causal set that's already grown, so it's, let's say, in the past of some of us now, for example, then the causal set elements and their relations, they are time. I mean, sorry, they are space-time. So they're if this is a successful, if this turns out to be a successful theory, then they will have a continuum approximation that's a four-dimensional manifold with a Lorentzian metric, and all of that information about the continuum is encoded in the discrete causal relations and the number of the space-time atoms. So that there's no super time there. There's no particular coordinatization. The causal set relations don't give you any preferred time coordinate. So yes, so I'm not sure I understand what Chris and Nick mean by such a concept as super time. And then the direction, well, there's a direction in the causal set, and there's a direction, I mean, the causal order relation in the block is also directed, and you make some choice of past and future direction in the block. That's, in the continuum, that arises because of the double light cone structure. At any point there's a past light cone and a future light cone, and you can make some continuously consistent choice over the whole of space-time if the manifold is time orientable, which we assume.
Yeah, okay.
And then the direction of the order of the causal set simply corresponds to the particular choice of the time orientation in the block.
Yeah, so this correspondence is sort of like a brute fact, or is explained by some, I guess that might be another way to put the question. So why it corresponds? I mean, just like from what?
It's what, so if you think in terms of continuum approximation to discrete underpinning, then you can say how is this continuum information encoded in the discrete structure? So part of the continuum information is this choice of time orientation, right? That there's for each event in space-time, there's a causal past and a causal future, and you can consistently choose past and future for each point. So where is that information encoded in the discrete thing? Well, it's encoded in the direction of the order relation. So it's not it's part of what you might call the discrete continuum correspondence. How is the continuum information encoded in the discrete structure, in the discrete data? So that's how it's encoded.
Okay, so it is like entails that by the directedness of the.
Yes, I think that's right. So yeah, because there's an order, a direction to the causal set order,
and that's entails.
It entails time orientation on there. Yeah.
Thanks.
So I have here Federico and then Christian.
Yeah, thanks. Thank you for the talk. My question arises from the fact I'm not familiar with this CSG theory you presented, so it's more of a clarification question. So in the graph, in the slide of the two graphs you presented.
Shall I show them again? Would that help?
Yeah, if you wish, maybe it's better for everyone. In both of the graphs, there were pairs of events which were causally and temporally disconnected, and like in the case of 2 and 3, and if I remember, they had a common effect.
I'm sorry, I'm just struggling to. Where is that?
If you have it.
I'm going to get rid of this now. That seems open, so let me try this sharing again. Sorry. Am I sharing?
Yes.
Yes, okay, good.
Yeah, thank you. It's not a very complicated question, but it's more easy for everyone to see. So where you have 2 and 3, for example, in the left graph,
yeah,
they are causally disconnected.
Yeah,
but they have they are both connected with 4.
right.
So I was just wondering if you can give an example of 2 such causally disconnected events which have a common effect, because I'm struggling in figuring out which kind of. So I understand that 2 and 3 are out of the light cone of each other, but somehow they cause the very same thing.
Good.
And then also, since I'm not familiar with the theory, which kind of causal theory, so what does it mean for the account of causality that, for example, if you have, are both 2 and 3 necessary for the happening of 4?
Yes, they're both necessary for the happening of 4.
Okay, so if you have no 3, then the causal relation in itself between 2 and 4 doesn't grant necessarily 4.
That's right.
Okay.
Yeah, 4 can only happen once 4 can only be born when 2 and 3 have been born. Okay. So an example. So here's the most challenging example. So suppose 2 and 3 are measurements of spins in an EPR experiment, right? So you set up some correlated state of spin, or let's say polarized photons or something. So in an EPR state, right? And then 2 and 3 are the space-like labs where the spin of one is measured in one lab and the spin of the other is measured in the other lab, in space-like to each other, so they're outside each other's light cones. But then 4 is where the experimenters come together in the future and compare their results, right, and publish a paper. So that's, yeah.
Okay, so
it's just something in the common future, in the common future of 2 and 3.
So it's strictly correlated with cases of that depends on quantum entanglement.
Oh, no. No, not at all. I just used that as a I mean, that's kind of always on the back of my mind, because everything I've told you today is all classical. This is a classical stochastic process. There's no interference. But at the back of my mind, there's quantum mechanics and the struggles that we have with understanding relativistic causality in the light of the Bell theorem. So anyway, I just gave that kind of as a joke, really. But no, it doesn't have to be. It doesn't at all have to have anything to do with quantum mechanics. It just 4 just has to be something in the mutual in the mutual future of 2 and 3. Just like 0 has to be something in the mutual past of 2 and 3.
Okay, thank you.
Okay, Christian.
Hi, thank you, Sylvia. Thank you for the talk. It was lovely. Thanks a lot. I think my question is sort of a follow-up to this one, so it's very perfect. The slide I need is this one. So my question was connected to the causal set as well. So maybe there's something I would like to understand better. Can you hear me well?
Yes, I can, yes.
So yeah, I have a question. Both questions were about the quantum, but one about the entanglement was sort of, I already had my reply. So the other one is still quantum. And again, it's my ignorance about causal set. I don't know anything about that. So I guess that in any approach to quantum gravity, there are going to be quantum phenomena that are explained. So it's still a quantum theory. So leaving entanglement aside for now, that I think I get it better. I was thinking about superposition for a second, and I was recalling that there were a couple of papers by Rovelli. So it's a different approach. Maybe this already explains. But he was talking about the possibility that you have superpositions of the observable connected to the length, to the Planck length. Which would entail, you know, way better than me, but this would entail that you can have superpositions of causal structure. He has a very nice quote where he says that the causal structure can be blurry. So if I look at the causal set, like the one we have in the slide, it looks like there is always, either there is no fact of the matter about whether the two nodes are one earlier than the other, or if they are connected, one is earlier than the other. This statement is right. Okay, so I was wondering whether having superpositions of this very tiny scale would perhaps put into question the fact that sometimes actually the events are in a superposition of being earlier and later. Is that possible? Because if it's possible, then this would be sort of counterintuitive with respect to the idea that there is this passage, because passage is supposed to be asymmetric, however you want to understand it.
Good. So the answer is we do not know at our current stage of understanding of quantum causal set growth. So the concept of superposition is perhaps not one that will arise in its usual form in a causal set theory, because superposition is a concept which arises in what I call a canonical approach to quantum theory, in which there is a Hilbert space, there are states in the Hilbert space, they're conceived of as states at a moment of time, and the superposition principle is then just that, you know, any two states, any two physical states in the Hilbert space, a linear superposition of them, a linear combination of them is also a physical state in the Hilbert space. So that all of that structure, Hilbert space structure, is tied to this canonical framework, where the basic entity is the state in Hilbert space, or wave function, and that is inimical to causal sets, and in fact a relativistic theory in general, but particularly to causal sets just makes that the problems of reconciling a relativistic perspective with that canonical view of quantum theory, causal sets makes that difficulty even worse. So to the extent that I don't think we're going to be able to say to build a quantum theory based on the notion of quantum state. So what do we have instead? What we have instead is the concept of the path integral. So the perspective that we adopt for trying to construct a quantum theory of causal sets is that the path integral is a much is a framework in which the fully relativistic character of reality in general relativity and in a quantum theory of gravity can be realized, in the sense that you don't need to think about the idea of a state evolving in time. So when I talk about the canonical approach to the canonical formalism for quantum mechanics, what I mean is that you take a classical theory and you identify a Hamiltonian. But to identify Hamiltonian, you have to identify time. You have to have a time coordinate, because the Hamiltonian generates evolution in time. And you have a configuration space of spatial configurations, and you have dynamical variables that are spatial dynamical variables, and they evolve in time. And all of that is just that there is no such thing in general relativity. That canonical picture of there being stuff, three-dimensional things, three-dimensional substance, three-dimensional structure, which evolves in time, all that is just not there. Whereas, as in fact realized by Dirac in a paper called the Lagrangian in quantum mechanics in 1933, the path integral is a framework in which you don't need to introduce any kind of preferred time, any kind of time slicing. You don't have to introduce canonical dynamical variables. You don't need a Hamiltonian. So in the path integral is much more adaptable to a relativistic perspective in which what's real is four-dimensional. So our perspective on quantum causal sets is that we need to construct a path integral for causal set. There you don't have superposition as such, but you have interference between different causal sets, so interference between different causal structures. And there our troubles really begin, because when you have two different so these are not just causal sets with different labelings. So here I've got the same causal set with different labelings. Now you have causal sets which are different. You know, there's no order isomorphism between them, right? But now the question is, how do you know whether one space-time atom in causal set number 1 is the same space-time atom as this space-time atom in causal set number 2? In fact, that's not knowable. I mean, that's not a physical. You can't say that. And in fact, you couldn't say it in two continuum spacetimes either. So, you know, how do you compare spacetime 1 with spacetime 2? What does, you know, what an event in spacetime 1 is the same as an event in spacetime 2? That is extraordinarily difficult to make sense of. So, yeah, so even before the sorts of questions you're asking come into play, which is, you know, you've got two events, and, you know, can you have a space-time in which those two events are ordered one way in one space-time and ordered the other way in the other space-time? What allows you to identify an event in space-time 1 with another event in space-time 2 in order to say that they're in different orders? You see, even that is not, I don't think that's possible. So what the question actually is, when struggling with the idea that you've got now interference between different causal structures, so different causal orders, different causal sets, that is, yeah, that's already very difficult. So you've opened the door now to a huge struggle that we're facing in interpreting quantum causal sets within a path integral framework.
Thank you.
Thank you for doing that.
That's it. I would be happy to ask you for references, but maybe I'll send you an email.
Sure.
Thank you.
So are there other people that would like to ask questions?
If there is time, I have another question on a different topic, but there are Alvaro first.
Yes, Halvor, please.
So I think I share more or less the same worry that Juliano was phrasing before. Did worry that a causal set is a space-time, a spatio-temporal structure. It has time and it has something like space. And then if we speak about a growth process for this spatio-temporal structure, it feels like this is a process in like an extra dimension of time. And I feel that the same is happening when we are going to speak about quantum mechanics with it. So yeah, I have this worry about meta time. And then, but you said something like, no, but this process is something like subjective because it's relative to the space-time atom in the causal set, which for me it sounds a bit strange to say that what exists is relative to space-time atom. So for me, either if I'm thinking in a block universe kind of thing, or in a series kind of, there is a space evolving in time. What exists is something objective that doesn't depend on a particular space-time point or a position in a space-time. So that is something that I find quite tricky about your perspective.
Yes, I'm not surprised. It is tricky. So, you know, in my very naive, cartoonish kind of understanding of, I don't know, philosophical perspectives on science, Western science, let's say, the goal of having a bird's eye view, a God's eye view, a picture of the world as it exists is something which is very prevalent, very a driving motivation, even, you know, something that people consider to be necessary in order for us to claim that what we're doing is, you know, is that science is objective. We're talking about the way the world is, that really, you know, that we're talking about the truth. So I think it's really, really difficult to accept or take on board or allow that physics is not going to give us that it gives us only a subjective view of the world as it exists, and that is what this theory gives us. So the process is objective. The process would indeed, as John Norton says, it would continue without us. Whether, you know, if we were to be suddenly snuffed out, the process would just, it's objective in that sense. It would just carry on. It doesn't require us to be here sitting experiencing anything to be physically real. It will just carry on. But the world as it is, that is subjective. So it's subjective to me. So for me, the world is the past. It's continually changing and growing because time is passing for me and more events are happening in my past. So, and that's the same for everything and everyone. And that you can't patch them together and give the global picture of the way that the world is, even one that's growing. That picture is you can't have it. And I claim, and I think Raphael Sorkin thinks the same thing. If you want becoming, and you want process, and you want to do justice to general relativity and the fact that there's no simultaneity, no global physical simultaneity, then the view of the world must be like this. You have no choice. You have to give up on the idea that there is a picture of the world you can have as it is. All you can have is a picture of the world as it is for me, subjective to me, to me now. And that's just my past. It's growing, continually accumulate, you know, sort of building up, accreting past for me, and the same for you, and the same for everyone, and that's it. There's no, yeah. So I agree. It's really difficult, and I think that it is a giving up on something that we have held dear for a long time as scientists, that we could achieve this view, and I think that you can't. And this is quite separate from the quantum, the struggles that we're going to have when we really tackle the quantum question, which are so great. It's quite terrifying, really. Yeah. Although there's a sort of hope there, which you see, because this view allows you to have both objective and subjective elements. You can have a dependence of what exists on each space-time atom, actually, or each observer, if you want to be a bit more coarse-grained. But it's also it's an objective theory. It has objective testable consequences that we can all agree on, so long as we're talking about things that have happened in our mutual past. Quantum mechanics could be like that. That again, in quantum mechanics, there's this struggle between objective and subjective elements. There's all the disagreements and struggles and debates about the interpretation of quantum mechanics. A huge aspect of that is, to what extent are we talking about something which is subjective? Can we only ever talk about things that we observe? Who's we? And right. So the hope there that you can have something which incorporates both, fruitfully incorporates things which are both objective and subjective. That you have to reconcile yourself to the fact that we are in the world, so there's going to be a subjective aspect of our physics.
Well, so the kind of interpretation of quantum mechanics I tend to favor also have this objective reality, be it many worlds, be it Bohmian mechanics. So these are the kind of theories that I say, okay, there is a real world. So I'm happier. Maybe this is my philosophical prejudice with an objective world. And for me, maybe when I hear this kind of presentations, for me it's too high a price to pay for saving this intuition of becoming.
I can understand that, and but if I say one more thing in favor of this view, which is that the subjective pasts, so my subjective past and your subjective past, they overlap, of course, because if they didn't, we couldn't communicate. Every word that I hear from you is an event that's happened in your past and in my past, right? And we agree on them because they are events that are concrete now and real in the past, which exists. And it exists in my past and exists in your past. And we, so it's not that these subjective points of view, are completely unconstrained, and it's, yeah.
Okay, thank you.
So Giuliano, do you have a question?
If there is time, otherwise do we have time?
Well, I think that we have other 5 more minutes, yes.
Okay. No, I mean, it's basically almost a follow-up of what you were saying. So I think that there are two notions of subjectivity that seems to be both relevant here. So one is something like dependent on there being consciousness or an observer, and the other one is being like irreducibly relative to a space-time point. So I think that in the theory, the only notion that actually do work is the second one, which is maybe, and it's the one that is, you can label subjective, but it's a bit of a metaphor, right? It's more like perspectival, rather than subjective. Because that would even, I mean, your theory could be true even if there's no conscious being in the universe, right? So that's, you don't need an observer, you don't need a measurement, you don't need, I mean, you just need that there is this irreducible relativization of existence to space-time point. But then exactly how these can by itself explain the experience of passage, which is subjective in the other sense. I mean, which involve a subject in the other sense, at least. So, I mean, my worry, and that's connected with actually what I mostly work on, is that you know, you could have a theory that explains the experience of passage, and only that requires only the resource of the block. And at this point,
sorry, say that again. You have a theory
of the experience of the passage.
Yes.
That only requires the theoretical resources that you find in the standard block view. So the only assumption that you make in order to explain the experience is something like the existence of space-time path in which there are conscious events, and that you have in both theory. You know, you have in in the standard block universe, and you have in your theory. So I don't understand exactly. So I understand the kind of like that's the sort of like story, you know, that your theory entails of what the world is like, maybe, you know, a bit more sympathetic to our naive view of how time unfolds, but that doesn't mean that it explains better our experience of time, because I mean, like it might be that, you know, that's so insofar as the fact that there are subjective in the sense of irreducibly relative to space-time facts, I mean, that per se doesn't still explain why my experience is in a certain way. And if in order to explain why my experience in a certain way, I just need there being these conscious events in space-time, well, that you have also in the block view. So I mean, I guess my question is whether, you know, whether the fact that there is this genuine becoming is really an explanatory advantage of the theory with respect to the experience of time. It might be you know, an advantage with respect to a lot of other things, maybe, you know, cosmology or whatever. I mean, like maybe we reach the great unification. So we may have all sort of other reason to believe in your theory. I'm not saying that that's but I'm just wondering, you know, whether explanation of experience can be one. Okay, because so it's too little to say that you know, there is this subjective things, because it's subjective just in this metaphoric way. Okay, sorry. That's
yes, I totally agree with your separation of the two notions of subjectivity, and the subjectivity is indeed of the second sort, where it's just what you, I think, call perspectival. Is that right? So it's, you know, it's,
yeah, perspectival.
It doesn't require any conscious beings, right? So if we're talking about experience, then of course everything is very slippery. What do we experience? Do you know what you experience? It's very difficult to pin it down, isn't it? So what I would say here is that what it explains is that we experience that we have the experiences. You see, because in the block describes the experiences already having been had. Because the universe has already run its course. So there's a series of books actually for children called, the first one's called The Lion, the Witch and the Wardrobe. Yeah. And one of the books is called, I think it might be called The Magician's Nephew. Anyway, in that particular volume, the children in the book find these magic rings. And if you put on one of the magic rings, then it takes you to what's called the wood between the worlds. And in the wood between the worlds, there are, it's this lovely forest, but there are these ponds, you know, little small ponds. And if you jump in a pond, then you go to a different world. So there's different, so they investigate some other worlds. But some of the ponds have dried up. So if you jump into one of the ponds with water, you go to a different world, which is, it's still in progress. Things are happening.
Okay.
But the ponds which have dried up, they're worlds which have run their course. They're over, right? Nothing is happening there anymore because it's all happened already. So the block is one of the dried up ponds. It's all over. It's all happened. And you can't explain having experiences if the world is a block. It doesn't describe experiencing one thing after another, actually having the experience. It's a record of them having happened.
I think it doesn't describe the way we think of the world given our experience, but that's still compatible with our experience being explained by just making assumptions that are the block view, and we are just, our narrative about how the world is just wrong. But anyway, that's a larger thing. So I don't want. Thanks for the example, and I understand your point. But I mean, of course, if it was, yeah, sorry. I just don't want to talk too much.
But as I say, to me, this particular question is unresolvable.
Okay.
I mean, it's this debate, you know, yes, it does, no, it doesn't, yes, it does, no, it doesn't. It describes things happening, no, it doesn't describe things happening. We can't get beyond it, in my view. I think, for me, becoming is a heuristic that will either turn out to be fruitful or not fruitful in development of quantum gravity. You know, I mean, all the quantum gravity ideas, causal sets included, are speculative. We don't know what will turn out to be the successful one in the end, and we'll judge what that has to say about being and becoming when we have it. So we'll look back and we'll say, yes, that was the right way to think because it led to this fruitful and successful development, and this was not the right way to think because it didn't produce any fruit. So I think it's premature for us to try to resolve this now. I don't think we can. I think, you know, our discussion here is just an example of how we can't, you know, there's just a claim that it does explain or it doesn't explain.
Yeah, no,
yeah.
Thanks. Yeah, I get that. Yeah, thanks.
Thank you. If there are no other remarks, I would like to ask one very short question. It's a pity that Daniel has an unstable connection because he is in my project is postdoc in ancient philosophy. And my question is related to the fact that you mentioned, Fay, in your presentation, xenoparadoxes. And I would like to hear more regarding this reference to Zeno, because we know that the paradoxes he dealt with were built up on, Greek mathematics, Greek foundations of mathematics, and there are specifically paradoxes that are built on the ambiguous notion of infinite. And so I would like to hear a little bit more from you regarding this reference to Zeno in your presentation. And why did you pick up Zeno rather than someone else?
I suppose, well, in choosing Parmenides to exemplify an ancient the point of view, the block point of view, I suppose Zeno immediately springs to mind as I understand it, which is not, you know, I haven't studied it, but Zeno was part of the school of Parmenides, so, you know, was a blockhead. And I think that the paradoxes were part of the argumentation that he made to justify this block perspective. So in that sense, I suppose I chose them because it seemed to me that he was, his arguments were, I mean, of course it's contradictory because there's a strange paradox of the stadium, which is very difficult to understand, but has something to do with discreteness even. So you know, there's contradictions within the paradoxes themselves, but one point of view is that some of the paradoxes, at least, are to do with, could be seen as arguing against the idea of the possibility of motion and change if the universe is a continuum. So I'm sure that's contentious. I'm sure that, you know, that scholars of the pre-Socratics will probably disagree, but they, yeah,
I'm sorry, because perhaps during the presentation I missed the exact link, so now it's a little bit clear, or it's clear the fact that you consider just the paradoxes dealing with you know, the problem of representing continuum.
The idea that infinitely many things have to have happened before the particular event that you're thinking about, like, you know, before you reach the halfway point, you have to have reached the quarter point. Before you reach the quarter point, you have to, right? So that paradox is a paradox of the continuum.
Yeah.
It doesn't arise if space-time, but space is discrete because you just make a finite number of steps before you reach.
You consider the stadium paradox, basically. You don't consider other types, so you consider that specific one.
I don't understand the stadium paradox, so I think I'm probably not. I don't want to base my my choice of Zeno on that one.
Okay.
But there's something about that stadium paradox which it's only a paradox if somehow, if you have something, if you have a continuum model of space in mind, whereas if you're prepared to accept a discrete model, then the paradox goes away. I think that may be so, but certainly the Achilles and the tortoise one, certainly it is Achilles and the tortoise, isn't it?
Yes.
Yes. Certainly is. That's again not a paradox if space is discrete. You only need to do it, you know, perform a finite number of steps before. You know.
Yeah. Well, thank you very much. Are there other questions or remarks? So, well, I thank again our speaker. Thank you, Fay, for having accepted the invitation. It was lovely to host you, and let's hope to meet in person at some point in the near future.
Thank you, everyone. Thank you, Sylvia, again for inviting me. It's been a pleasure.
Thank you. Thank you. Thank you all. Bye-bye.
Bye. And yeah, email me if you have further questions.
Thank you. Bye-bye.